So we have a nice straight line graph showing that the equation is correct. Force is equal to a multiplying factor, the spring constant, times the extension. In this case we get 4 centimetres of extension for every newton, so this spring constant would be a quarter, or 0.25. And the reason why it's a nice straight line is because we're still in what's called the elastic or Hooke's law regime. If we overstretch the spring, if we put too much mass on it, then it will extend further than it should do, and it will not go back to its original shape. I'm going to sacrifice one now for the good of the experiment. If I overstretch this spring, as you can see, it won't go back to its original shape, and it will extend a lot further than it should do. It's not quite broken, but the atoms have moved around and they won't go back to their original shape. Now, what I've found quite useful for classes as well is to see the overall effect. So if I come over here, I've got a series of springs as identical as I can get them, and I've got the different masses hanging off each one, starting from 100 grams and going all the way down to 700 grams, which is still within the Hooke's law or the elastic regime, and you can see the length that the spring has become going up. So if you were to subtract the extension, the original length from each extension, then you'd have a graph. It's almost as if we're looking at that graph upside down. And that's all there is to it. Good luck.